we continue our discussion on classification and prediction models. Previously, we had seen that we had used an support vector machine, a linear discriminant, and its extension the kernel machine, where we have the nonlinear surfaces as our classification boundary. So, we had kind of two classes or more classes, and we want to separate them out by drawing a class boundary. And one of the way we saw was to use the support vector machine, a linear discriminant, which is having the highest margin. So, what we will do in our next 3 lectures is to use another paradigm where we tackle the same problem of classification, of putting an object into one of the k classes. In fact, we can actually use this to a more broader class of problems known as the prediction problems, where it is not just the class levels that we can predict, but also if some real value. So, for example, the temperature of a place tomorrow, some real value, not class, that we can also do with this paradigm. I will explain how to do that. So, this new paradigm we are talking of falls under a general umbrella of what is called a artificial neural network. The main reason for that is that it came from a inspiration from the biological neurons. Okay. So, it was one of the popular artificial intelligence algorithm in very early in computer science, in the 50s and 1950s, 1960s is became a popular. So, the motivation was you can perform a complex prediction task by connecting together a number of simple units, simple computer processing simple units known as neurons, with connections between them known as synapses. And this was kind of considered to be large scale parallel processing. Lot of units come together, simple units come together parallelly, do a task, and in a distributed manner solve a problem. And it had some nice properties, like it was robust, it was robust to both noise and failures, and that a whole group of algorithms came to be known as neural networks. Okay. So, as I have said that it is kind of a mimic of the natural neuron, the biological neuron, which has lot of connectionism. It can do very complex tasks like face recognition, audio recognition. We sort of try to replicate it in a computer model by, I will explain, by something called a simple neuron unit, and we can sort of tune the connection weights so that we can perform a desired task. So, let me to motivate come to the structure of a basic biological neuron. So, it has a structure like this. So, it has two parts, axons and dendrons, okay, and these are the neural cells. Okay. So, what happens is that as a input signal, a stimulus comes, say from the eye, say some light cell, some visual the stimulus comes, it travels through this axons, and where it gets inhibited or enhanced by some factor. So, here is the stimulus, let me call it as input, and this is the connection, and each connection has a weight, it increases or decreases x. And then what happens is that this cell body it receives lot of such connection, it does two operation, it adds them up, add of inputs, aggregates the inputs. So, it will have multiple such neurons connecting to it, it will add up all these things, and then it will apply some kind of threshold. That means, if it exceeds certain value, it will fire. So, it will have a threshold, and if the sum of the inputs exceed that, it will fire. What is meant by fire? That means, it will send another signal to the next level of neuron, which will again travel like this. Okay. So, for example, our eye, say we see some stimulus, this is our eye, and some signal goes to some neuron, which processes it maybe from lot of other neurons, sends it to the next neuron in the brain, which sends to other neuron in the brain, and finally, some task is, say we recognize it as a person, as a face of a person, that happens. Okay. So, this is kind of, there are much more complications in this, I am only giving a simplified view, it is much more complex, but this is the broad picture. So, as I have said, these are dendrons, cell body, axons, and synapses where they connect to each other. Okay. So, they carry electrical signals in a nonlinear way and affect the next level. Okay. So, this is this nature of the connection and the strength of the individual synapse, which I call as weight, which decide finally what action it will take. Okay. So, this model is found that it is a good thing to mimic. Okay. So, it can do well in lot of tasks where you have lot of high dimensional input. For example, so many visual inputs are coming, so many pixel information are coming, all type of input, different type of complex functions, there this kind of model is powerful. So, we will henceforth not refer to the biological neuron, we will refer to something called a I'll explain what is a artificial neural network, what is the exact computer model network or NN. It is a popular data mining tool. Data mining tool, right. So, we will explain what it is. As I have mentioned, you can use it. In fact, it has been particularly you should. So, this is another sort of advice that only when you have a really complex problem, because neural networks will usually require more computational time than other algorithms, and that is why I am treating it towards the end of my this is the last classification algorithm that we will discuss. You use it only in the problems which are the hardest, most complex, like driving a car and other things, only there you use it. Okay. So, given this, now let us start with the simplest artificial neural network model, which we call as a perceptron. It kind of mimics the earlier biological neuron that we talked about. Okay. So, let us see what this is. This is the entire structure of a single perceptron. Step by step, let us see what it is. it takes a number of inputs x 1, x 2, x n, as many inputs as you want, okay, which can be anything real valued, usually it is real valued. There are some models where symbolic values are taken, but usually it is real valued, x 1, x 2, x n, some input values. So, these input values may be length of a person, suppose I am categorizing a person, weight of a person, or say credit card for detection, what is the income of that person. Okay. So, these are the or we can also call it as attributes, or these are also called features. Okay. Then each of these input is multiplied by a weight of the connections. Each input is connected by this arrow to the main neuron, each of these are connected. These we call as connections, and each connection has a weight which we call as connection weight. There is one kind of dummy input x naught, which is always set to 1, which is called a bias. And also similarly, there is a weight W naught, which is the bias weight. Okay. Then let us see what this threshold, what this neuron does. So, what this neuron does, it is a sigma operation, it just adds up these weighted inputs. So, it just computes this term, weight into the input, weight into the input, okay, over all the inputs in fact actually you can write it down, and it adds up the bias term, bias weight W naught. So, actually you could have, so this is the bias, in fact you could have also thought of it like this, that summation I equal to 0 instead of 1 0 to n W I, which includes W naught and x I x naught is always 1. You could have also written it like this. Okay. So, this is the output of this aggregation unit. Okay. This is the output of this. So, then there is another unit f, or the activation function. The input to this unit is the summed up input, weighted sum of the weighted inputs, including the bias. Okay. And the output is some function of this summation I equal to 0 to n, okay, that is the some function, some f, some it is as if some function it applies on this summed up inputs, weighted inputs. So, this activation function is very important. it can take different forms. Here is one particular form. So, its value of the output of the application activation function is 1 if the input is greater than positive, 0 minus 1 otherwise. So, it looks like this. If summation w I x I equal to 0 to n, if it is positive, it gives plus 1, negative it gives minus 1. Okay. So, this particular form has a special significance. I will explain what the significance is. The significance is like this. Let me call as the output as in fact, let me write it this way. X naught is 1. So, into 1, in fact, I can erase that. Like this. So, if there are two terms, say 2 inputs, I will have things like and y is some. So, this f is a threshold function. How does it look like? If this quantity is negative, it is minus 1, positive plus 1, this quantity. It looks at the x, not x rather, this looks at some kind of I, some input, let me call it as u. So, this quantity if I call as u, so this u is on the x axis and it thresholds it. Now, this is a geometrically, if I look, it is a familiar form. So, greater than 0 is plus 1. So, if this equation of this line is zero, so all this here will have y equal to plus 1 and all this here equal to y equal to minus 1. Okay. So, this thresholded activation function is nothing but a linear discriminant. So, let me again write down this, so you remember it. F takes this form, okay, and you have I am expanding for 2 input features, you can extend it to multiple features also. So, this is not, this is this, on this I apply f which gives either plus 1, y equal to plus 1 or y equal to minus 1 depending on the sign of this quantity, greater than 0 or less than 0, this function. Okay. So, perceptron can be thought of as a linear discriminant function with threshold activation function. In fact, there is a slightly different way of looking at it. Instead of having W naught as a separate term, you can also have it like this, a shifted threshold. Shifted threshold where this is W naught, your bias term, bias rate. Okay, this amount of shift. All right, but in general, you can have other forms of activation function. Okay, so this is what I have seen. In fact, this particular way, let me explain you. This particular way of writing meant it can be, it was originally used to use perceptron as a logic gate. Logic gate. Let us see how to do that. Suppose I have two inputs, two weights, and there is a bias term W naught, and there is a threshold activation function. So, what I want this final y as some logical function of this x 1 x 2, say x 1 and x 2. Okay. So, if we say that x 1 x 2 takes binary values 0 or 1 values. So, that means when this is 1, this is 1, output should be 1, all other cases output should be 0. Is a AND gate. So, I can make this perceptron act like an AND gate by choosing W 1, W 2 and W naught properly. Okay. So, can you tell how? Can you tell a value when this will happen? Let us see. Let me draw again. Y. So, what I want? So, let me choose a value of W 1, W 2. So, let us say, let us try this. If W 1 is 1, W 2 is 1. Okay. So, if this is say 1.9, what happens? When this is 1, this is 1, this is 1, when this is 1, this is 0, this is less than 1, sorry, this is not 1.9, this is minus 1.9, less than 1, and so less than 0. So, this will come to minus 1 side, or say 0 side, this will become 0. So, let me actually, sorry, let me, in fact, I can choose this at like this also by convention, and I can do that. Okay. So, these values minus 1.9, 1, 1 makes it AND gate. You can realize other logical functions also. threshold is this, threshold or sometimes called step also is like this. Shifted threshold is like this. It's like this, approximation of that. Okay, so you can choose, but this is the most common. In fact, the original definition of perceptron meant this only. Okay. So, I hope the overall architecture, so to say, the function is clear. Next class we will talk about how to tune the weights to perform a task. Thank you. I am to break নিয়ে আবার আসছি গো।